Okay, so here is our second topic for this unit. We're talking about the atomic structure and the periodic table, and in particularly I'm going to introduce you to what's called electron configuration. That basically dictates where all the electrons are within these orbitals of an atom. So if we have something like carbon, that has 6 electrons, where are each of those 6 electrons? We've started to look at that when we looked at quantum numbers. Now we're actually going to be able to start sort of to draw where each electron is within an atom. So if we look at our learning goal for today, it says that by the end of today, you should be able to use the Pauli exclusion principle, Hund's rule, and the Aufbau principle, and the location of an element on the periodic table to use that information to write electron configurations. So I know that all these terms are new. Pauli exclusion principle is new, Hund's rule is new, Aufbau principle is new, and even electron configurations are very new. So we're going to go through and explain each one individually, and then in class we're going to practice putting it all together and writing it out. Okay, so first thing, energy levels. We have some rules when it comes to energy levels, okay? Here are the rules that you sort of need to keep in the back of your mind, and these will sort of become second nature to you as we progress through some of the problems that you're going to see. So first off, energy levels of the lowest energy are filled first. So here we have got the first energy level, or the first period on the periodic table, that has the least amount of energy. Electrons are going to fill that first before going on to the second energy level, before going on to the third. Okay, so in this diagram here, this is an energy level diagram. We go from low energy up to high energy. So 1, which is the lowest, up to, in this case, 6, which is the highest. When your n value increases, the energy of an electron also increases. So if you have an electron in the second energy level, those electrons have more energy than electrons that are present in the first energy level. Within one energy level, third point, the energy increases in the subshells from S to P to D to F. So that means electrons that are in the S subshell have less energy than electrons that might be in a P subshell, and have less energy than electrons that might be in a D subshell, etc., etc. Now you're going to see a little bit of quirkiness happening here. Here we've got a 4s that actually has lower energy than a 3d, and we're going to talk about why sort of later on. Alright, so some more rules with energy levels. As we saw in the last lecture, as atoms become larger, the main energy levels actually become closer and closer together, and we get that overlap, that crazy picture of overlapping orbitals that I would never expect you to draw. Some sublevels start to overlap in energy, so this chart below helps you memorize the proper filling order of orbitals. So if you draw out your orbitals, so just do 1s, 2s, 3s, 4s, 5s, 6, then there is no 2p orbital, but you can have a 1p orbital, but there is a 2p, 3p, 4p, 5p, and 6p. There is no 1d or 2d orbital, but there is a 3d, 4d, 5d, and 6d orbital. And then what you do, if you actually start drawing arrows this way on a diagonal, that will tell you the order that they fill in. So the 1s orbital is going to get filled first. Then we end at that arrow. So then we go back to this arrow here at the beginning. The 2s orbital gets filled next. Then the 2p orbital gets filled, then the 3s orbital, then the 3p orbital gets filled, then the 4s orbital, then the 3d, then the 4p, then the 5s, then the 4d, then the 5p, then the 6s. So it kind of ends up in a wonky order. It doesn't always go just from number 1 up to number 6, okay? We do kind of have a lot of overlap happening. This chart is only meant to help you to memorize the proper order so that when you're doing problems you can figure it out quickly. Alright, so let's start filling orbitals with electrons. There are rules. Here's the Aufbau principle, the Pauli exclusion principle, and Hund's rule that you're going to need in order to create these energy level diagrams and draw electron configurations. That was our learning goal. You need to know these 3 rules. You will be asked them on a test. So the first, the Aufbau principle. Electrons will always occupy the lowest available energy level. We've already talked about that being a rule, so that's what the Aufbau principle is. The Pauli exclusion principle says that no 2 electrons have the same set of 4 quantum numbers. And we started to look at that at the last lecture when we were looking at your N, L, ML, and MS values. If you look at those values, at the way they work themselves out, there are no two electrons that have the same 4 quantum numbers. That's the Pauli exclusion principle. Last, Hund's rule. Electrons remain unpaired for as long as possible. So we talked about how we can have an MS value. I'm going to write with my mouse here. MS value of +1 or +1/2, or you can have it to be -1 or -1/2, okay? And we talked about this sort of being in the clockwise direction and this sort of being in the counterclockwise direction. That's the only way that two electrons can be paired together, is if they have opposite spins. If they have the same spin, they're going to repel each other too much and they're not going to want to pair up. Again, because electrons are negatively charged, they want to remain unpaired for as long as possible. So we're going to fill up all the positive values for MS first, and then we're going to go and fill up all the other spins, the negative values. I have seen textbooks using circles or squares, if you want to write that in, or a square. Ooh, this is very hard to write using a mouse pad. I shouldn't even bother. Okay, you guys can laugh at me in class. So you can use circles or squares to represent orbitals, and arrows represent electrons when we draw these energy level diagrams. So let's start. We're going to go through the first few elements of the periodic table. So we're going to start with hydrogen. This here is sort of a good example of what your Bohr-Rutherford diagrams would look like when you were drawing them in grades 9, 10, and 11. We know now that it's more complicated than that, but just for simplicity's sake for today, I'm going to use them. Okay, so we know hydrogen has 1 electron. Here it is. It's in the lowest energy level, N equals 1. Okay? When we write out its electron configuration, we call it 1s1. The 1 in front of the 1s1 means that this is the quantum number N equals 1. It's in the first energy level. So that's what this 1 means. So this 1 means that it's in the first energy level. The S means that that electron is in an S subshell. So that means this electron is in a subshell that is in the shape of a sphere. That's what your S tells you. This 1 here means that there is just 1 electron in that orbital. Okay? And the reason why we know that is because hydrogen only has 1 electron. Okay? If we were to draw the energy level diagram, this is what I would expect you to draw. Okay? So in this case, you can see here's a square representing the energy level. Okay? It's labeled 1s, okay? Which again means N equals 1. And S means it's the S subshell, it's in a sphere. Okay? The arrow going up indicates a spin of +1 or +1/2. Okay? Whether the electrons actually spin is debated when they're all by themselves, but it is one property of the electron's configuration, and we're going to kind of stick with that principle. Okay? When N equals 1, so when you're in the first energy level, your L value has to be 0. Because remember, L cannot be, L has to be whatever your N is minus 1. So 1 minus 1 is 0. Okay? So that means that you only have an S subshell. Okay? And you cannot have any arrows in the 2s box. So here's the 1 arrow representing the 1 electron for hydrogen, and it's in the 1s subshell. Let's look at helium. So helium, we know, again, has 2 electrons, okay? Again, here's a very simplified diagram of what helium looks like, okay? We know from grades 9 and 10 and 11 that both of those electrons are in the same energy level, okay? They're both in the N equals 1 energy level. Okay, so again, here's the 1, and that goes with your N equals 1 energy level, okay? Because N equals 1, we have to have an L value of 0. This is what we did yesterday. If L value is 0, we know we have an S orbital. So that's where we get the S from. And the 2 again denotes that there is 2 electrons in that orbital. Okay, 1, 2. So our electron configuration for helium is just 1s2. Our energy level diagram has a 1s2, okay, there's the electron configuration above the diagram, but it's basically a box, and it's got, in this case, 2 electrons in it. One electron is spinning in one direction, say the positive direction, and the other electron is spinning in the negative direction. So we've got one arrow going up and one arrow going down. We have no more electrons, so we have no electrons in the 2s or the 2p subshells. Alright, this is lithium. Okay? So lithium, again, the first 2 electrons are still in that first energy level, just like helium, okay? So these 2 electrons are the same as helium. So those 2 electrons are here in the 1s2 subshell, okay? But we have a third electron in this case. Where does it go? Well, there's no more room here, so it goes to the next energy level, okay? And we know that. Remember the 288 rule from grade 9? We know that the electron has to go into the next energy level. So here it is, it's gone into the second energy level. We're still in an s orbital, okay, and we only have 1 electron in there. There's my 1 electron, it's drawn with an upwards arrow. So my electron configuration is actually 1 s 2 2 s 1. So I basically take these 2 numbers here and combine them to write my electron configuration. Alright, next one in the periodic table, beryllium. We've got 4 electrons now. Again, you're still going to have 2 in the 1s subshell. Now we're going to add another electron, okay? What's going to happen is the electron in the 2s subshell is going to get filled first. So this second electron is actually going to go into the 2s and not into the 2p. Why? The off-bow principle. Electrons will always occupy the lowest available energy level, and we also said that an s orbital has less energy than the p orbital. So if we've got another electron in there, the electron is going to fill up the s orbital before it goes into the p. Okay? So when we draw our electron configuration, hopefully you can figure this out by now, we have 1s2, indicating 2 electrons in the 1s subshell, and 2s2. 2 electrons in the second energy level in the s subshell. Next up, boron. Same idea, but in this case, your 2s orbital is full. So the expansion begins into the 2p orbital. This orbital still belongs to the n equals 2 subshell. Okay, so this third electron here is actually kind of got to go into this ring. But we know now that it's not just going to go in a nice pretty circle around, that it gets more complicated than that. So it's actually going to go into a p orbital, which is those dumbbell shapes. Okay, so it is drawn as a particle in the upper image up here. Okay, but it actually has that dumbbell shape of a p orbital. Okay, and notice that the p orbital only occurs when you have an L value of 1. Okay, so this electron here has a different set of quantum numbers than any of the other electrons before it. Okay, and we put it, because there's only 1 for the p orbital, we're going to put it in that first p orbital there. So our electron configuration, I'm not going to write it because it's messy, so it's 1s2, 2s2, 2p1. That's our electron configuration for boron. Next up, carbon. Electron configuration is written at the bottom here. Okay, you don't have to draw 2p1x, 2p1y. That's just getting very specific as to which orientation you're using. You can write it as 1s2, because we still have 2 electrons in the first energy level, 2s2, and then you're going to write 2p2, because you have 1 more electron in the p subshell. Now, why did I put it here and not here? Again, if we go back to our rules, electrons remain unpaired for as long as possible. That is Hund's rule. So Hund's rule says if electrons have to remain as unpaired as long as possible, that means if we've got this energy level here that we can fill up, these other orbitals we can fill up, the electrons will be much happier there than anywhere else. So I'll just erase that because that's not right. Okay, so that's why we put the electron there first. Okay. If we check out the next one, if we check out oxygen, okay, oh, we skipped nitrogen, but that's okay. Check out oxygen. Oxygen has an electron configuration of 1s2, 2s2, and now how many electrons do we have in the 2p subshell? 2p4. So that's your electron configuration, 1s2, 2s2, 2p4. And here I drew one electron in this p orbital, one electron in this p orbital. One electron here would have been nitrogen. Now we're getting full with our p orbitals, right? In our different orientations. So I have to pair up this oxygen, this electron for oxygen in one of the p orbitals. I could have drawn it here. I could have drawn it here. But I didn't, okay? I drew it there, okay? It doesn't matter where you draw it, though, okay? Ideally, you should fill up the first box first, but that's okay. All right, and last one, neon has a full set of energy levels, okay? Its electron configuration, 1s2, 2s2, and now I've got 6 electrons in the 2p subshell, so 2p6. So we sort of rushed through the last couple examples there, but that's okay. We're going to go through more detail in class, okay? Last thing I want to show you is a pretty picture of the entire periodic table with the S, P, D, and F blocks, okay? What you guys are going to learn to do is to basically be able to look at anything, such as magnesium, on the periodic table and be able to write the electron configuration of that, okay? So for magnesium, the electrons in magnesium, well, the first one started up here, 1s2, then we've got 2s2, then 2p6, then 3s2. That would be the electron configuration for magnesium. So we're going to learn about that as we go through stuff in class. Okay, shorthand electron configuration. Okay, what we can do is we can actually use the preceding noble gas in brackets. So boron can actually be written like this. Okay, so boron, we can use the preceding noble gas, which is helium, and then write the rest of it. So we're basically, instead of writing 1s2, we're calling that helium, because that's the electron configuration for helium, and then we're writing the rest, 2s2, 2p1. Now it seems kind of silly, but when we start to look at all the other ones here, here's oxygen, here's fluorine, so you can see that's actually not too bad. Here's neon, here's the next noble gas, okay? 2s2, 2p6, okay? So we could also use this as sort of your baseline for the next row. Again, we'll go through a bunch more examples of this in class. Alright, last couple of slides explaining the periodic table. The maximum number of electrons in the s, p, d, and f orbitals corresponds exactly to the number of columns of elements in the s, p, d, and f blocks on your drawn periodic table. Okay, so if you ever want to figure out how many electrons a p orbital can have, you can count the columns on your periodic table. You can count that there's 6. That means there are 6 possible electrons within one p orbital. Okay. Here's an example of transition elements, are elements that fill the d energy level. Okay, so the 5d orbitals can accommodate 10 electrons, and there are 10 elements in each transition metal period. Alright, so now that we know a little bit more about the electron configurations, we can use them to explain why the ions in your transition metals are kind of unusual, and why we use the periodic table to determine what the ion charges are. So let's look at zinc for my first example. So zinc has an electron configuration of argon as its noble gas, and then the rest of it is 4s2, 3d10. Okay, for something to lose 10 electrons and empty out this subshell, that's kind of difficult to do, but it's really easy for zinc to lose maybe 2 electrons here from the 4s subshell and become zinc 2+. So that's when that's one of the reasons why you won't see zinc with a 1+ charge on it. You'll see it more so with a 2+ charge. Here's lead. Now, if you guys look at your periodic table, you know that lead can have a charge of 2+ or 4+. Here's why. In order to go from your baseline lead, here's your electron configuration, so to go from that to lead 2+, we lose the outermost electrons, a 6p2. Okay, so we lose those 2 electrons, and then we get a 2+ charge. Okay, then to lose 2 more electrons and go to the 4+ charge, we actually use lose, the 6s2 electrons. So your final electron configuration is what's remaining. Your argon, or not argon, sorry, your xenon, noble gas, your 4f14 and 5d10. Okay? Electrons from the highest energy levels are usually lost first, so that's why again we lose the 4, because the 4 energy level is a higher energy level than the 3, so we're going to lose the 4 first here, we're going to lose the 6 first in both of these cases here. Alright, some unexpected electron configurations are copper and chromium. Okay, and we're going to talk about why these have some unexpected electron configurations. We know chromium here, if we just follow the rules that I've taught you so far and you write out your electron configuration, you're going to see that it's got a 3d4 and a 4s2. Okay, but in reality it's 3d5 and 4s1. So we actually take an electron from the 4s subshell and put it into the 3d subshell. Why? An electron is basically borrowed from the 4s subshell and placed in the 3d subshell, okay? And this is because this is the reason why. We're going to talk more about this in class, but I'm just going to give you a quick explanation here. It says half-filled and fully filled subshells tend to be more stable than something that maybe is not half-filled or not fully filled. So you want a subshell that's fully filled, completely empty, or half-filled. That's more stable than not, okay? Alright, here's a periodic table. I'm going to give you a copy of this in class, and it's got all the electron configurations for every element on the periodic table, okay? So you can see sulfur is 3p4, okay? It also has, yes, 3s2 in there, so it just kind of gives you the end part of the electron configuration, but at least it helps you out a little bit. And that is all for today.